So I put up an example of a typical, well, maybe not a typical exponential growth problem. Usually exponential growth problems have to do with growth of bacteria in a petri dish, or radioactive decay of an isotope, or the decay of medicine in a person's bloodstream. So I thought we'd try something a little different. Let's talk about balloons. So to celebrate John's birthday, his wife ordered 10,000 balloons for his party. After the party was over, the balloons started to pop, and the number of balloons decayed exponentially, such that after 6 hours there were only 2,500 balloons left. So, how many balloons were there 10 hours after the party is over? So what we know is that 6 hours after the party is over, there were 2,500. So we know is that the number of balloons was 10,000, and now it's 2,500. And so that ratio equals 1/4. So what we can say is that there are 1/4 as many balloons every 6 hours. Now, how do I know it's every 6 hours rather than just after the first 6 hours? The answer is in this phrase, that decayed exponentially. Recall that was the definition of exponential growth or decay, is that every some period of time we multiply the amount of something that we have by the same amount. So every 6 hours, the fact that in the first 6 hours we multiplied the original amount of balloons by 1/4 means that every 6 hours we're going to multiply it by 1/4. So what that means is that the number of balloons, the amount of balloons, is given by the starting number of balloons, which is 10,000, times 1/4, and we simply need to raise this to an exponent. If I raise it to the exponent t, where t is the number of hours, then that means that every hour I'm going to multiply 10,000 by 4, and that's not what I want to do, because what we know is that it's only every 6 hours that we multiply the original amount of balloons by 1/4. So instead, what I have to do is take this exponent and divide it by 6. That means that every time t goes up to 1, 2, 3, 4, 5, 6, this exponent goes up by another integer. So what this would mean is that if, let's say, example, t equals 6, this equation would be a equals 10,000 times 1/4 to the 6 over 6, which is 10,000 times 1/4, or 2,500. So as you can see, it actually does work. If I use this equation, I get the exact numbers that I have in the problem. And of course, if t was 12, then this exponent would be 12 over 6, or 2. So then I'd be multiplying the original amount by 1/4 times 1/4. Okay, so now let's just calculate with the amount that's requested in part A. So how many balloons were there at 10 hours after the party is over? So that's just going to be the situation where t equals 10. So we know the amount of balloons will be the starting amount, 10,000, times 1/4 to the 10 over 6. And that I've already calculated. That comes out to approximately 992 balloons. Okay, so that's one type of word problem that we may have to solve involving exponential growth or decay. In this case, decay. So let's go to the next type. When will there be 500 balloons? So what we know is that the equation that gives us the amount of balloons is a equals 10,000 times 1/4 to the t over 6. And what we know is that at some point there are 500 balloons. The amount of balloons is 500, so we simply want to plug that into the equation for a, the amount, and then solve for t. So 500 equals 10,000 times 1/4 t over 6. And now I'm just going to divide through by 10,000. 500 over 10,000 equals 1/4 to the t over 6. Now, this is equal to 1/20th. Alright, so now what we need to do is extract that t from the exponent. There's no way to do this other than to use a logarithm. So what we want to do is we want to get rid of this 1/4 to the something, and because we just want the t on the other, we want the t and some simple factor on the other side of the equation. So what I'm going to do to get rid of this 1/4 base is I'm going to take the log base 1/4 of both sides of the equation. Now, please, 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 please do not let it freak you out that I'm using a fraction as the base of the logarithm. We already talked about how the base of an exponential or logarithmic function can be any positive number except for 1. So there's nothing wrong with having a base of 1/4, and as you'll see, the change of base formula makes it very easy to deal with. So I'm taking the log base 1/4 of 1/20th on the left and the log base 1/4 of 1/4 to the t over 6 on the right. That gives us log base 1/4 of 1/20th on the left, and log base 1/4 of 1/40th to the t 1/4 to the t over 6 is just t over 6. That was the whole point of using the logarithm, because it extracted that t from the exponent. I multiply both sides of the equation by 6, and I'm going to turn it around so t is on the left side. So this is going to be t equals 6 times log base 1/4 of 1/20th. Now, by the way, if this was a test that had no calculators, which in fact you would be unlikely to be asked for a calculator type answer, this would be a complete answer. But let me show you how you can get the answer on your calculator, knowing that that there is no log base 1/4, but there is a natural log and there is a log base 10. So I'm going to use the natural log to do that. I'm going to use the change of base formula to get 6 times log base 1/4 of 1/20th is the natural log of 1/20th over the natural log of 1/4. That's your change of base formula. And I have calculated this already, and this comes out to 12.97 hours. So that's when there will be 500 balloons left.